Hey everyone, this is Dr. Keith. The purpose of this video is to give you a little extra help on the clustering algorithm in Tableau. Now they do have this nice video here, a quick intro to clustering, and I know they have more here on their website, but I wanted to boil down a few of the useful features together into one shorter video that gives more detail than this one here alone. That might be useful for you and show you how I do clustering and sort of the iterative process that I go through. Anyway, I'm going to open up a data source. This is one that came from Microsoft a long time ago on their old SQL Server Analysis Services add-in to Excel, and I've gotten a lot of great use out of this. Anyway, this is a data set of people who have purchased bikes, or sorry, these are people who have gone into a bike store, and supposedly some bike store owner gathered information on them. Things that would be relevant to explaining whether or not someone purchased a bike. Marital status, gender. I went through, and for purposes you'll see in a minute on the video, I turned some of these variables into numeric variables, like gender, 0, 1, marital status. I think I just made it, even though there's many different options. Oh no, they just have single and married. So I changed that to a 0 and 1. They've got income, number of children, age, whether or not they own a home, education, of course, whether or not they purchased a bike, and I've also got a numeric version of that one here. So let me show you what I want to do. Hopefully you've already read or gone through some background on what cluster analysis is, and I'm not going to go through all that. I just want to show you how it applies in Tableau. So we can use actually both numeric or categorical variables, but the algorithm that Tableau uses is the k-means algorithm with a Euclidean distance measure. And that means that these measures are going to be much more reliable, although we can use dimensions too. So let's start with something simple like age and children. Okay, now Tableau is going to give you, because they're numeric variables, the sum of each of these, which isn't particularly useful, and then sum them all up and plot them. So age, if you add up the age of everybody, of all 1,000 people in the data set, because I know there's exactly 1,000 people in the data set, this means that the average age is going to be somewhere around 44-ish. But because it's the sum, it's 44,000. Anyway, same thing with children. Total children among all these people, it looks like it's about 19 or maybe 2,000 children. Anyway, this isn't what we want. What we're going to do here is come up to, and you can't see it because I'm on a Mac, but if you go up above here to your analysis option, deselect aggregate measures, and that's going to show you every single case plotted here on the map at once, on the graph at once. Now we could do things to this to show different colors, shapes. Don't worry about that for now. All we want to do here is go to analytics, grab cluster, and drop it out here, and it's going to pop open this nice little box. So it says we're going to automatically choose a number of clusters. Now the k-means algorithm, if you know much about that, you actually have to predetermine the number of clusters you want. However, Tableau has a nice technique they use to automatically determine that for you, and they basically take the within cluster distances divided by the between cluster distances. You want higher ratios that are better than lower ratios, and they calculate that ratio for every combination of 2 through something like 50 clusters or something like that, and see which ratio is the highest, and then they say, okay, the highest ratio is when we divide it into 3 clusters, so that's what we did for you. Or if you have some theory that tells you it should just be 2, enter that number in. You know these features probably already, or 5. I'll stick with automatic, that's fine. So let's do this next. I'm going to close this out and go to describe clusters, and this is the information I want to talk about that's very useful. So summary information, yeah, that's cool, but here's what's super useful. Clusters 1, 2, and 3. And it's going to describe them for me. So this is actually it's a center of the sum of age. So actually this is really kind of like an average age. It's one way to interpret it. So cluster 1, these are 36-year-olds. Cluster 2 and 3 don't really differ a lot in terms of age. But when you add that with children, then what we get are 35-year-olds with very few kids, 50-year-olds with a lot of kids, 50-year-olds with average number of kids. Now, one more, and then what we can do is we can use this to describe our clusters and remember who these people are. Now, you can check this box, which basically says give us standardized scores between, I don't even actually know what the standard is. I think it's something like 1 and -1 if it's similar to other calculations. But I don't particularly like this. I like looking at the actual raw data, raw averages. Anyway, click here now on models, and this is also incredibly useful. What this is saying, now this is, it's one way to interpret this is an F statistic and p-value. The p-value, of course, we're looking for values lower than 0.05, and this one, it's so small, they've just rounded it basically to 0. What this means is the difference between those three clusters in terms of the number of children is statistically significant, meaning that the number of children is a significant factor to differentiate among clusters. So is age. Age is also clearly different among the clusters. Now you might remember, well, wait a minute, these two are very similar though. When we're talking about this is basically a one-way ANOVA. And if you're taking my class right now, at this point you may not have learned what that is, but we'll go into that more a little bit later. But a one-way ANOVA is basically just a way of saying, okay, let's look at the average ages for these three different clusters, and it's kind of like doing a t-test to compare the differences between them and say, is there a statistically significant difference between those clusters? And as long as there's a difference between this one and this one, or this one and this one, the overall one-way ANOVA, F and P value, it's still going to be statistically significant, even though two of the clusters are very similar. That's not a problem. So that's interesting, but I'm not going to stop there. There's many more relevant factors data that I have access to besides just age and number of kids. So let's add a few more here to the cluster. I'm going to go back and hit Edit Cluster again, and let's add some variables. So let's add number of cars and see what that does. Oh look, pull back out. We just went from 3 clusters down to 2. I can just tell by the colors right here. Let's close this and let's take a look at the detail. Describe clusters. Okay, so now I've got my age has changed. It's only 2, and it's gone up to 37, up to 51. So I've got younger people with no kids and 1 car, and older people with 3 kids and 2 cars. All right, let's check our models again. Looks like all, again, very significant p-values, meaning that each of these variables plays a large role in separating out these 2 clusters and maximizing the distance between those 2 clusters. That's how I interpret. So a p-value here means that children, age, and cars, again, a p-value meaning below 0.05. A p-value below 0.05 means that that variable is a significant indicator or a separator of these clusters that pushes them further and further apart. So let's add another variable. Edit clusters. Let's add in, what do we got next here? Let's add in income. Okay, let's describe that one. All right, now what do we have here? Okay, ages they're moving a little bit, but about the same. Children about the same. Cars about the same. But now we have income. So again, this one's gone a bit smaller. That one's gone a bit bigger. But now we can clearly see, all right, these are younger people, fewer kids, fewer cars, less money. Just think logically. Does this make sense? It does, right? If we're younger, we're going to have fewer kids, or maybe make less money. If we have less money, we'll have fewer kids, and we're going to buy fewer cars. So far, these variables are moving and describing the way we'd expect them to. But let's add one more, and here's where it gets kind of interesting. Grab up here, we're going to grab a dimension. Grab purchase bike. Oh, sorry, hold on. Edit cluster. Then grab purchase bike and drop it in here. Okay, that changed things quite a bit, didn't it? You can see just by the colors changing. So let's describe this now. And now I've got, okay, age has changed quite a bit. Well, why is that? Well, so have children. I've got those who are barely older here, barely more children, barely more cars, less income. But here's what it does with a categorical variable. It says, okay, what's the most common category that they fit into? Well, these are the people, slightly more kids, a little bit older, more cars, less income. These people are not buying bikes as much as these people. But you know, again, limitations of the k-means algorithm with categorical data. I don't want to get into the details of why, but one problem is it doesn't tell me like how yes and how no that is. It could be that 51% of cluster 2 bought a bike, so it put yes, and 49% of cluster 1 bought a bike, so it put no. I don't know how close those are like I know how close these are. So what I can do instead is come back here, edit my clusters. I'm going to remove purchase bike and instead use this measure version of purchase bike where I coded 0 as didn't purchase, 1 as purchased. So it's going to turn out exactly the same, but the advantage is I can come here, describe cluster, and now it tells me, oh, I was hoping it would give me an average. Evidently, oh no, it does. These are the people, so sorry. So that purchase bike was, and again, this is part of the problem of having it's not really a continuous variable, it's a dichotomous variable, it's only a 0 or 1. This is playing a much larger role in forming the clusters than these variables are because there's only 2 possible values of it. So its first takeaway is that it's not super valid to use the k-means cluster to include variables that aren't continuous numeric variables like these ones are, but that's fine. It's better than nothing still. Anyway, people who don't buy a bike are those with this much income, slightly more cars, slightly more children, slightly older, whereas the people who do purchase a bike are these ones right here. So very useful information. Let's go to models though now and take a look at it. So this says, okay, purchase bike, you can see by the non-existent p-value, that's the biggest factor in driving the separation between these 2 clusters. And again, this is a bit artificial because there's only 2 values, and it's not as smooth and continuous as some of these others. This number, again, remember, this is scientific notation. This means to the negative 10 means that this number is actually 0.0000000002724. So it's very small and close to 0. Again, bigger F statistic means we're going to get a smaller p-value. Children, statistically significant, even though what's interesting, look, the difference, let's do cars first. The difference in number of cars doesn't look that big. Same thing with number of children and age. None of them look that big. Well, the thing though is when you have a lot of cases, we have 1,000 cases, or 1,000 data points in this case, you can still get very small p-values. So just because a p-value is small, that doesn't mean that there's really a whole lot of difference between actual practical difference between the values in those 2, in that factor between the 2 clusters. Now, here's what's interesting. Sum of income, this p-value is not significant. It's above 0.05. If you were just to start with this model right here, you would look at that and wonder, well, wait a minute, why is that? I mean, the percent difference from cluster 1 to cluster 2 in income is fairly similar in the percent difference in age, right? This one, the percent increase from here to here is actually pretty similar as from here to here. Well, remember, in previous iterations, those who were older, had more kids and more cars were actually making more money. And this time, when we include purchase bike, they're making less money. What does that tell you? It tells me that there's a lot of variance in income. Income varies quite a bit, whereas these 3 variables tend to vary together a little bit more. Age, children, and cars. Whereas income, it does increase with age, children, and cars, but not as tightly, or it's not as highly correlated with those. So even though the difference between them is roughly similar to age, it has reversed. And because there's a wide variance in income, it's no longer a significant predictor of whether or not you'll belong to cluster 1 or cluster 2. So the key takeaways from this video, I might have lost you at a couple points, but here's what I want you to learn and remember. First, when we do cluster analysis, do it iteratively. Sorry, I don't know how you want to say that word, but anyway, add 1 variable in at a time and watch and see how these statistics change. See how it changes the cluster. In practice, there are many different clustering algorithms. K-means that Tableau uses just one of them. There's many different distance measures. Euclidean distance that is used by Tableau is just one of them. But K-means and Euclidean distance are probably the 2 most common, and they're safe across a wide variety of contexts, which is why Tableau chose to use them. If you want to get much more advanced and accurate with your cluster analysis, you're probably going to need to use a different tool. But for all intents and purposes, most cases, most scenarios, you're not going to get a whole lot more accurate. Or at least Tableau is good enough and a good enough start that it's worth learning this tool and being able to use it. Okay, hope that's helpful.